Welcome ICS4U folks. This is our first lesson in our unit on searches and sorts, algorithms. And we talked a little bit last year about algorithms in grade 11, but this is going to be kind of a big boy and big girl version of that. We're going to sort of be more particular in what we talk about as far as an algorithm is concerned, and also pseudocode later. So here we go. You have this file, or you should. Please just add to it as you see fit. I'm going to try and go fairly quickly so you have some time to get to the exercises. An algorithm, and this is the definition you saw last year. An algorithm is a finite set of rules that gives a sequence of operations used to solve a problem. And we talked about last year what finite means, and a sequence means this, then that, then the other. And we're going to expand on this definition, and we'll see some very specific examples as they pertain to computer science algorithms. Now, when you hear to solve a problem, well, what's a problem? We think of math problems or problems in life, but essentially in computer science, we just think of some way from connecting inputs and outputs. So we have some sort of input, we have some sort of output, that's a problem. Okay. If we talk about an instance of a problem, that's a specific example or case of a problem. So we'll have an example here in a second. A problem is like the big picture, an instance is the small picture. When we could think of the problem as the class and the instance as the object, if you want to put it in OOP terms. Sample problem. So here's a typical one from this chapter or this unit. Given a non-empty array of numbers, find the largest number. That's a problem, right? Where the input is an array of length n greater than 0. Notice that that's an assumption that we're making in this problem, that we've actually got a non-empty array. And if we had an empty array, we would have to change our algorithm to deal with that instance, the instance of having an empty input. But in this case, it's not empty. And the output is the largest number in A. So this is just finding the largest number in an array. And that's one of the things you did in your review project. So the instance, the specific case of that, would be here's an array, and find the largest number of this array. The input is this, and the output would just be the largest value. The output would be 6 in this case. And that's it. This is an instance. We'll also think of this as a test case. There's lots of different types of problems that we'll use algorithms to solve, and I'm going to go through these quickly. There's decisions. For example, are these numbers in order from smallest to largest? This sounds like, and it is, a Boolean that is the output. True, false. Yes, no, that sort of thing. Search, return the smallest number. Well, this was the one that was in the sample problem. Optimization, find the 3 numbers with the largest product, right? This is like a find the best answer. And certainly, this one sounds more difficult than this one, and it is. Counting, how many even numbers are in the set? This is just counting the number of solutions. Enumeration is actually listing those solutions then. And these are all different types of problems that we might be asked to do to find an algorithm to solve. What makes an algorithm good? So there's all sorts of algorithms, and we weren't worried too much last year about what a good algorithm is. But we will worry a little bit this year. We won't evaluate algorithms. I'll leave that for your university computer science classes. But you should have some instinct about a good algorithm. First of all, it's got to be correct. It's got to give you the right answer. It helps if it's fast. And this is, how do I determine whether an algorithm is fast or not? Well, again, that's a thing I'm going to leave to your university professors. Okay, we'll actually talk about it just a very little bit in this chapter, but it'll be kind of a strange evaluation that we'll do of the quickness. An algorithm is good if we can use the algorithm on any instance. We talked about our earlier problem not dealing with the empty set, for instance. This has a computer science term to it with abstraction. Does your program or does your algorithm work on any test case? The algorithm on any size of instance. So scalability. Does this work on really, really small cases or really, really big cases? This is the idea of scalability of an algorithm. Use the algorithm within another algorithm, modularity. And this is what we practice when we write functions and procedures called methods in Java, right? Modularity. Can I grab that and put it in a different algorithm? And that's what makes an algorithm good. And of course, we often use pseudocode to express an algorithm, usually as a stepping stone before we write code. It's hard to go from a complex problem straight to code. So pseudocode helps. And we've done a little bit of pseudocode, and we kind of did a not very good job of it, and we're going to do a better job of it now. We're going to put on our big boy pants or our big girl pants and do a decent job of pseudocode, and we're going to talk about that in video 2.